Hello friends, apart from the previous lecture, when we largely discussed about the mechanical condition, what we primarily meant was tensile loading. Now there is a significant amount of similarity between the way we impose tensile loading or compressive loading. Now if you consider uniaxial tensile loading, that is, you have a sample and along the length or the longitudinal axis of the sample, you are imposing a compressive or rather a tensile load. Now the same load can also be imposed by fixing one end of the sample, one longitudinal end of the sample, and applying the load on the other loose end. Now in the same manner, we can introduce or we can impose the compressive load just by reversing the direction. So what we need not do is, we need not change the way we position the sample. So this is a significant similarity between tensile and compressive loading. That is, the way we handle the sample does not really change much, but the direction of load gets reversed. In the same manner, it is also possible for us to introduce torsion loading as well. So it is possible for us to introduce the torsion loading in the same manner. So by supposing if you have an equipment and that equipment handles the sample in a specific way, like we have seen here. Now particularly if it is possible for us to handle the sample along its length, then it is possible in that equipment to impose tensile load, compressive load, and also torsion load. Now in the previous lecture, we considered a different form of a mechanical condition. What this mechanical condition involves is, we are fixing, for our understanding, we considered a different way of handling the sample. So we want to understand this unique mechanical condition that is much different from compressive tensile loading. So in order to understand that, we considered a different way of handling the sample that is distinguishable from the way we handle the sample when considering tensile or compressive loading. So when we want to impose this new form of this unique loading condition, we fix the sample not at a specific longitudinal end of the sample, but along the longitudinal axis or along the longitudinal direction. So here it is at a longitudinal end, and here it is along a longitudinal axis. So on longitudinal axis, what we mean by that is, it is along the length. So we are fixing the sample along the length, and the load is being applied here on the surface. The load is being applied, and in response to the load, the material, it behaves in a different manner. The way the material responds to the load is considerably different from what we observe during tensile or compressive loading. So in red, we see how the material responds to this form of loading condition, and this load is what we refer to as the shear load. And the way we quantify the response of the material to this shear load is by largely focusing on the shift in the corners. So initially the corner A was in this position, and now the corner has assumed a new position of A prime. So therefore the response of the material offered when you impose a shear load is proportional to the shift in the corners that we have quantified as the distance between A and A prime. Now if we want to talk about the strain, if you want to have, or if you want to express the response that is independent of the dimensions of the sample, we take the ratio of the shift in the corners to that of the dimension, the original dimension of the sample. That is, we take the side that experiences this shift. We consider the side that has moved away from this point to this point. So the length of the side is OA. We take the ratio of the shift in the corners with respect to the side wherein we are able to observe this response. So it is the side OA that helps us observe, or that helps us notice this material has responded. So therefore we take the ratio of the shift in the corners, which is the characteristic response that the material offers to shear loading, and we normalize it with respect to the original length of the side, which has now distorted in response to shear loading, and this is what we refer to as the shear strain. This is represented by delta. Now, we also saw that in addition to the shift in the corners, there is a loss in the orthogonality. That is, when you consider these two sides, let me highlight it in green. So when you consider these two sides here, this side and this side, these two sides were perpendicular to each other. They were orthogonal to each other. Now there is a loss in the orthogonality. So even here there was these two sides were perpendicular. There was a 90 degrees angle that was subscribed in this region as well, in this point as well, and this has also been lost. So the orthogonality is lost in response to the shear load. So there is a shift in the corners and there is also a loss in orthogonality. So therefore it is possible for us to describe the response of the material to shear loading in terms of this loss of orthogonality. So to quantify this loss of orthogonality, we are considering this angle here, that is theta, and when you consider tan theta, considering this triangle A prime is a right angle triangle. When you consider tan theta is nothing but A prime by OA, which is equivalent to the shear strain that we observe. So the shear strain can be defined in two ways: shift in the corners and the loss of orthogonality, the angle that is introduced because of this loss of orthogonality. And in most cases, since we are largely focusing on the elastic region, and therefore the shift in the corners is minimal and correspondingly the angle is close to zero. This can directly be tan theta, we saw that can directly be treated as theta, and therefore it is equivalent to that of the shear strain. So the angle that is introduced because of the loss of orthogonality, if you could consider, if the loss of orthogonality has not appeared, then this angle would be 0. So this angle assumes a value because this orthogonality is lost, and this angle is nothing but it is one way of quantifying the shear strain that we observe. Now, when you want to have a completion of the description of the mechanical behavior, we saw that we need two components. One is we need to quantify, we need to be able to express the mechanical condition, and we need to be able to express or describe the response of the material to the imposed mechanical condition. So when you want to discuss mechanical behavior, we need two components: a way to express the mechanical condition that we impose and the response offered by the material. So now what we have here is, we have two descriptions, that is the ratio of shift in the corners with respect to one of the sides, the shifting sides of the sample, and the angle that is introduced because of the loss of the orthogonality. So both these, they described shear strain, which is nothing but the response offered by the material. Now what we have not considered is how we can present or describe the shear load that we have imposed. The shear load that we have imposed is nothing but the load that is applied on the surface, or rather that is applied on the surface. But again, we saw that when we are considering or describing the mechanical condition in terms of load, there is a difference. When we want to use this load to describe the specific mechanical behavior, then it again is influenced by the dimension of the material. So therefore, in case while we were discussing about compressive and tensile loading, we translated the shear load to stress, and this stress, we saw it is the ratio of the load to the cross-sectional area. Now the reason why we consider the cross-sectional area is primarily because when you impose a loading condition such as this, when we impose a loading condition, so let's consider the tensile loading condition, the resistance offered by the material is dependent on this cross-sectional area here. So let me repeat, when you impose the tensile load, the resistance offered by the material is dependent on the cross-sectional area. So meaning, when you increase the cross-sectional area, correspondingly the resistance will also increase. Why it is dependent on the cross-sectional area? Because we have this atomic bond that is associated with the cross-sectional area. When the number of atomic bonds increases with the cross-sectional area, the resistance offered by the material to the tensile loading also increases. So therefore, the cross-sectional area influenced the amount of load that is required to bring about the desired response. So when you desire a response and you impose a load for it, the amount of load that is required to bring about the desired response was dependent on the cross-sectional area, and therefore to normalize this load, we took the ratio of load with respect to the cross-sectional area. So it all depends on the parameter that influences the resistance to the imposed loading condition. In case of tensile loading, it was the cross-sectional area that imposed the resistance to the tensile load, and with increase in the cross-sectional area to achieve the desired amount of the response, the load needs to be increased, and therefore we took the ratio with respect to the cross-sectional area. Now if you take that understanding and if you place it here in case of shear loading, it is no longer this cross-sectional area. This is no longer this cross-sectional area that brings about, or that rather resist the deformation, that resists the response of the material when you impose a shear loading condition. It is no longer this cross-sectional area that resists the response offered by the material. So, however, what we observe is, when you want to slide this sample, when you want to achieve a deformation of this sort, as opposed to this cross-sectional area, it is this cross-sectional area along this direction here that brings about that establishes the resistance that is offered by the material. So to make it clear, we have a sample that is fixed along the longitudinal direction. Now it is possible for this given sample or for us to calculate from this given sample two cross-sectional areas. So one is this cross-sectional area here, and other is this cross-sectional area here. So depending on how you slice the sample, it is possible for us to have two different cross-sectional area. Now when you impose the shear load, the deformation is of this sort. So what we observe is, we observe a response of this sort. For this response, the resistance, this cross-sectional area offers no resistance, or the resistance offered by this cross-sectional area is rather minimal, because all this cross-sectional area is doing is, it is just inclining. However, when you consider this cross-sectional area, what is happening is, you see a sliding action in response to the shear load. So this cross-sectional area, that is say O prime, all this cross-sectional area is doing is, it's just reorienting itself, it is not deforming. However, when you consider this cross-sectional area A prime, what it does is, it is rather along this cross-sectional area there is a sliding event. So therefore, when you are imposing a shear load, the resistance is not offered by O prime, but rather it is offered by the cross-sectional area A prime. So therefore, correspondingly, when you want to describe the shear stress is nothing but the load, the shear load that is imposed, and the area that offers resistance. It's the ratio of the shear stress that we impose and the area of resistance. Now in this case, the area of resistance is perpendicular to the area that we usually consider for tensile or compressive loading. And when you consider the appropriate area, then we would end up with what we refer to as the shear stress, and this is the expression for shear stress. And in this case, the shear stress is the ratio of, so superficially it is the ratio of load with respect to cross-sectional area, but which cross-sectional area is a point in question, and here the cross-sectional area is, this area is associated with the cross-section A prime. So this is how we describe the shear stress associated with the shear loading condition. So the definition of the stress remains the same. So what changes when you consider shear loading is, what is the area that we are considering? The area that we choose should depend on the resistance offered by the material. It should this area should influence the response offered by the material. When you have this larger area, there is a larger resistance offered by the material. When the area along the axis A prime is higher, the larger resistance is offered by the material, because of the same rule or because of the same condition that the atomic bonds that resist the behavior increases. So what essentially we have is this sliding event that using which, or the sliding event which characterizes the response of the material to the shear loading, it is this resistance to the sliding event rather is offered by these bonds along the AA plane. And therefore, as the area of this AA plane increases, the resistance correspondingly increases. Therefore, when we are quantifying the shear stress, we need to consider this area instead of the area that we have been considering so far, instead of the cross-sectional area that we have been considering in the context of tensile and compressive loading, because this area no longer imposes any resistance. So the resistance offered during this response comes from the cross-sectional area along A prime plane. So therefore that area needs to be considered. So this is what distinguishes a shear stress from that of the tensile or compressive stress. In both these cases, superficially the expression remains the same. It is load per unit area. But which area distinguishes the tensile stress from that of the shear stress? Now, within the elastic limit, when you consider within the elastic limit, the elastic limit is characterized in the similar way for the tensile, compressive, and also for the shear loading case. So it means the stress is proportional to the shear stress is proportional to the shear strain that we observe. So the shear stress is proportional to the shear strain that we observe when we are operating within the elastic limit. So the constant of proportionality that relates the shear stress to that of the shear strain is referred to as the shear modulus. So this is something that stems up from our assumption that we are operating within the elastic limit. So the response offered by the material in terms of the shear strain is proportional to the shear stress that we impose. It's linearly proportional to the shear stress that we impose. So when you replace this proportionality strain with a constant of proportionality, this constant of proportionality is nothing but the shear modulus. So far what we have seen is, we have seen different modulus. So different moduli. So when you consider tensile or compressive loading, we have seen there is Young's modulus, that is represented by letter E. And when we are considering not the response in a specific direction, but the response of the material holistically, the volumetric change exhibited by the material, we saw there is an equivalent constant of proportionality called bulk modulus, which we represented by K. And now when we extend our consideration of the shear of our mechanical condition to shear loading condition, we have arrived at shear modulus, which is represented by the term G. Now in one of our lectures, we were able to establish a relation between these two. Now the reason we need to understand, or we need to relate these different moduluses or different moduli, is primarily because there might be cases wherein it is possible for us to only through experimental settings, wherein, so there might be experimental setting, we would be having access to few experimental setting or one of the experimental setting which allows us to calculate only one of these material parameters, material properties, and from that machine, but what we desire is to find the other one. Let us take an example. Supposing if you have an equipment that allows you to calculate Young's modulus precisely, but it doesn't have any feature to calculate the bulk modulus. So in that case, when you have an accurate estimation of the Young's modulus, the relation that we have derived helps us translate or helps us estimate the corresponding bulk modulus from the Young's modulus alone. So you have a machine, it can calculate only Young's modulus, but what you desire is bulk modulus. Since you already know the relation, it is possible for us to calculate the bulk modulus from the Young's modulus. So the experimental setting or the study that we are doing should not restrict us in achieving our desired goal, and this relation helps us achieving our desired goal, that is to know the bulk modulus from the calculated or from the observed Young's modulus. Now in that case, it also becomes necessary for us to relate the Young's modulus to that of the shear modulus. So when we have an expression for relating Young's modulus to that of the shear modulus, then it becomes easier for us to estimate one from the other. So if a given equipment gives us one property, it will be using this relation, you will be able to estimate the other property as well. So in order to do that, in order to relate the Young's modulus to that of the shear modulus, let us consider the deformation that we observe, that distortion that we observe during or when we impose a shear load. So we need to make some approximation to make our derivation rather easier. So one of the approximation that we make is we are considering a simple sample that is in the shape of a cube. So we are considering a simple sample that is in the shape of a cube. Now let us name each of these corners A, B, C and D. Now because of the imposed tensile loading, or rather because of the imposed shear load or the shear stress, what we observe is there is the shift in the corners of C and D. The corners C and D have shifted. So this is what we refer to as the shear distortion or shear deformation. So the corner D has shifted to D prime, the corner C has shifted to C prime. Now when we want to define the shear strain associated with this distortion, it can be expressed as D prime by AD or C prime by BC. So we have considered a cube sample, and now we have imposed a shear load. In response to the shear load, the shift in the corners has occurred, and now we have described the shear strain based on the shift in the corners. Now we need to relate the shear strain. So what our ideal goal is, we need to arrive at a relation or expression that relates Young's modulus to the shear modulus. So we need to relate Young's modulus to shear modulus. So what we need to have then is, we need to identify a distortion, a deformation that is similar to the ones that we observe during tensile or compressive loading. Because we need to relate Young's modulus to shear modulus, we have started with the shear deformation, but since we need to include the Young's modulus, which is exclusively associated with tensile or compressive loading, we need to identify a distortion in this sample that is similar to that of the tensile and compressive distortion. So tensile and compressive distortion, what it essentially happens there is a elongation or a shrinkage of the length. So therefore we need to identify such an element in this sample which exhibits an elongation or a shrinkage in its length. So let me repeat, what we are attempting to do is, we are attempting to relate shear modulus to the Young's modulus. Shear modulus exclusively associated with shear strain, Young's modulus exclusively associated with tensile or compressive strain. Now when we want to relate it, we already have introduced shear distortion, but when we want to introduce in this context Young's modulus, we need to identify a portion of the sample that exhibits elongation and or compression. Only then we will be able to introduce this Young's modulus in this context. So in order to do that, it is possible for us to identify one of the element that is easy for us to describe, that exhibits the expansion or compression, so that both exhibits an elongation or the shrinkage, and also it is possible for us to quantify it. So we are now trying to identify an element in this sample that exhibits either expansion or compression, and it is possible for us to quantify this. Now if you consider the sample here along with the shift in the corners, you could see this diagonal that is AC is now AC1. So the diagonal of the element which was originally AC is now AC1. So what we see is this diagonal, noticeably it has increased its size. So it is something similar to someone stretching this diagonal to EC1, so stretching this diagonal AC and then just placing it here so that it is along this horizontal line. Let me repeat, when you compare AC to AC1, noticeably the AC1 is of a larger size when compared to AC. Now this AC1 can be achieved, so this orientation of AC1, this inclination of AC1 or this diagonal can be achieved by stretching this AC and then inclining it in such a way that both AC and AC1 are along the same horizontal plane. Now, when we do that, when we consider, so what it essentially means is you increase this length of AC and then you incline it in such a way that it is along the same horizontal plane. Now, in that case, what we have done is we have stretched the diagonal AC. So, this is the description of the shear strain. We will let it be. Now, what we have done is we have elongated the diagonal AC. Now, the strain then associated with AC would be the new length the AC has assumed, that is AC prime, minus the original length AC with respect to its original length AC. So, what we have done is we have considered an element, that is diagonal AC, that has exhibited a stretching. So, stretching means there is a load that is acting on AC that allows this AC to stretch like we observed during the tensile loading case. Now, the reason we call it as stretching is because it is possible for us to conceive that the same change in AC to AC1 is like stretching and then realigning it in a different angle. So, this is the expression that we get when we want to quantify the strain that is associated with AC. Now, in addition to AC, there is also another diagonal, that is BC, rather BD. So, this BD has also experienced a distortion and it is now BD. So, originally it was BD and now it has experienced a distortion. So, what has happened is from BD, the diagonal is now BD prime. Now, this distortion is not elongation, but it is in response to a compressive loading. It is a shrinkage which we can attribute to a compressive sort of loading that this diagonal experiences. So, AC, it experiences a tensile form of a loading. So, therefore, it moves from AC to AC prime, and here the BD, it experiences a compressive sort of a loading. So, therefore, it moves from BD to BD prime, and this BD prime, the new diagonal, BD prime is less than BD, whereas in case of AC, the AC prime is greater than AC, because AC, the diagonal AC, is experiencing a tensile loading, whereas in case of BD, the BD is experiencing a rather a compressive loading. Now, what we observe is this AD and BC, these are two diagonals within a square. So, it means that AD and BC are perpendicular to each other. The AD is perpendicular to BC. So, whatever strain we observe, that is, whatever strain we observe along AC can be, it is the resultant of two strains. So, let me repeat, what we have is, we have two elements BD and AC. These two elements are perpendicular to each other. So, we have two elements, that is AC and BD, and these two elements are perpendicular to each other, and these two elements are experiencing a loading condition that is similar to tensile and compressive loading. Now, when you consider the deformation of AC, so this deformation or the strain along AC, this strain is the combination of the direct strain, that is due to the load along AC, and an indirect strain that is due to the Poisson's effect of the deformation of BD. So, what we have is, we have an elongation of AC in a specific direction. Along the perpendicular direction, there is a compression. So, it means the compression of BD will also contribute to the elongation of AC. So, we have two perpendicular axes. So, we have AC and BD. So, there is a tensile load that is operating in this direction. So, there is an expansion along AC. However, in addition to the tensile load, we see that there is a compressive load that is acting along. So, there is a compressive load that is acting along BD. So, this compressive load that is acting along BD will also contribute to the expansion of AC. So, the expansion of AC, the strain along AC, therefore, is the combination of the direct load that is acting along AC and the indirect response along AC because of the compressive load along BD. So when you consider the compressive load along BD, because of the Poisson's effect, there will be a resulting tensile load along AC. So therefore, the strain that we observe along AC is the combination of the direct strain, the combination of the direct tensile load along AC, and also the indirect response due to the compression along BD. Now, when we want to quantify the direct response, it is nothing but we can quantify it in terms of the load and the associated moduli. So in this case, we are considering the tensile load and we have only imposed the shear load here. This shear load is what translates to the tensile load along AC. So let me repeat, we are imposing only the shear load, and this shear load is what translates to tensile load along AC. So therefore, we can write the direct response of the AC as the ratio of the load, or rather the stress and the corresponding modulus, which in this case the stress that we have, the only stress we have is the shear stress, and that is what translates to the tensile stress along AC, and the moduli is the Young's modulus, because we have a distortion along the longitudinal, along the lengthwise, or along the lengthwise. So there is an increase in the length of AC, so the corresponding moduli is the Young's modulus. So what we observe is the direct response that contributes to the overall strain along AC is the ratio of the shear stress and the Young's modulus. So we have identified an element in the sample that is exhibiting a shear distortion, and this element is experiencing a strain, and that strain is along the length of this element, and this strain is contributed by two factors. One is the direct stress that brings about this increase in length. The other is the compressive stress along the perpendicular direction, which due to the Poisson's effect brings about an increase in this particular direction. So that is what we have seen here. So the direct response of this element, the element AC, for the imposed shear stress is expressed in this manner. Now when we want to calculate the indirect response, we need to go for the Poisson's effect. So when you consider the Poisson's ratio along AC and BD, so since the Poisson's ratio is negative of the strain that you observe in the perpendicular direction to the strain that you observe in the loading direction. So the Poisson's ratio is the ratio of minus the strain that we observe in the perpendicular direction. So we are focusing on, for the Poisson's effect, we are focusing on BD. So it is the strain that is experienced along BD. So this will assume the role of the denominator. So this is the strain along the loading direction. This will assume the role of the denominator. But so the numerator would be the strain along the perpendicular direction. So it will be epsilon AC. So this is indirect strain. So we are considering the Poisson's effect with respect to the axis BD. So when you consider Poisson's effect with respect to the axis, this axis is BD. So when you consider the Poisson's effect with respect to this axis BD, then the Poisson's effect is the ratio of the strain that we observe in the perpendicular direction. The perpendicular direction for BD is AC. So that strain is indirect strain. So that is why that comes in the numerator. In the denominator, we have the strain because of the loading. So that because of the loading in that particular direction BD. So that is the direct strain that we observe here. Now, from this expression, we have the negative sign here. From this expression, the indirect strain AC is nothing but minus the direct strain along the other diagonal and the Poisson's ratio. Now, whenever you have an expression for the direct strain, it is rather straightforward. We will be able to calculate this direct strain because it is nothing but the ratio of So we are considering the direct strain here. It is the ratio of the stress the particular sample experiences with respect to the corresponding moduli, and here again we are considering a compressive sort of a deformation, so the modulus remains the same, and the only stress that we are considering is the shear stress. The only stress that has been imposed is the shear stress. The reason that the reason why we have compressive action because of the shear stress is because this shear stress translates itself to the compressive load along this particular element. So we are considering elements wherein the shear stress translates to either tensile load or the compressive load. But here, since it translates to a compressive load, we have a negative sign. We need to introduce a negative sign. So we now have an expression for the direct strain along BD, which has the load and the corresponding modulus. And when you substitute this here, what we end up having is, we end up having an expression shear stress, Young's modulus, and the Poisson's effect. So what we ultimately have is, we have now an expression for the direct strain along one of the elements that we have considered and the indirect strain along the one of the elements that we have considered. So we have a couple of expressions. So we have two expressions that relates. So the direct strain along the element that we have considered and the indirect strain along the element that we have considered. So therefore, the overall strain along that particular element is the sum of the direct and the indirect strain the element experiences. So when you sum up these two, we will be able to arrive at an expression for the overall strain the material this particular element experiences. So it will be, and when you take the shear stress and the Young's modulus out, you will end up with an expression something like this. So this is the overall strain, the particular element that we are, the diagonal element that we are interested in experiences. So this is one of the critical relation that we are interested in. So now what we have observed is, we have considered a strain along AC and we were able to arrive at an expression for it. The overall strain along AC, now we are able to arrive at an expression for it. Now when you consider, so let us go back. So what we have essentially done is, we have considered two sections, two elements of the sample, and we are able to see that this sample, these elements that we have considered in this sample experience tensile and compressive loading. So therefore we were able to introduce the Young's modulus in this context. Well and good. Now let us go back to the deformation, the deformed sample here, the distorted sample here. Now in this distorted sample, let us consider a point E. So let us consider a point E. This E is perpendicular, so CE is perpendicular to the AC prime. So that is one feature of this point here that we have considered, and this E has another feature associated with it, that is, so CE is perpendicular to, or since we have already used C as Young's modulus, let us call this as O. So CO is perpendicular to AC prime, and the other property of this CO is, the CO is equal to AC. So we are selecting a point O along AC prime, and the reason the characteristic feature of this point is that it is equal to the original diagonal length of the sample. So we have selected a point O along AC prime, and this point is the original length, or this point, it sections the AC prime in such a way that AO is rather the length of the original diagonal AC. So this rather the AO, pardon me, the AO is the length of the original diagonal AC. So in the new diagonal AC prime, we are selecting a point. The reason we are selecting this point is because we need a section of the new diagonal which is the length of the original diagonal. So we have AO which is similar to, or which has the dimension that is identical to the original dimension. Now what we have essentially done is, we have sectioned then AC in AC prime the new length into two, that is AO and OC prime. So therefore the AC prime So AC prime then can be expressed as this. AC prime can be expressed as AO plus OC. And since AO is equal to AC, the AC prime can be represented as AC plus OC. So this entire AC prime we are expressing, we have selected a point O that is equal to, so when you this point, the reason we have the characteristic feature of this point is AO and AC are equal, and from this point we have two segments. Because of this point we have two segments, and therefore this AC prime can be expressed as AO plus OC. And now what we are doing is we are replacing this AO with AC, and we have now an expression for AC prime that is equal to, we have an expression for AC prime which is equal to AC plus OC. Now when you consider the deformation, that is the deformation along AC, when you consider the deformation along AC, the one that we have considered here, it is nothing but this we have already expressed here. This deformation along AC is AC prime minus AC by OC, or rather AC. This is we have already considered, because we are considering a diagonal element AC which has increased its length by AC prime. So with the increased length, the deformed length assumes the first position, the original length assumes the second position, and it is taken the ratio, we are taking the ratio with respect to the original length. Now we have an expression for AC prime by introducing a point O along the AC prime. So this expression we will substitute it here. When you substitute this expression AC plus OC minus AC by AC, what we end up having is the strain along AC is nothing but the ratio of OC by AC. So if you consider, consider this expression here, that is the strain along AC is OC by AC. That is the strain along this is OC, the change in the dimension with respect to the original dimension OC prime, rather it should be OC prime by AC. So, yeah, so it should be OC prime, that is OC prime by AC. So in this case AC prime we have sectioned it into AO and OC prime. So we have this length here, so we have this green diagonal here, and we have also a point O in this green diagonal, in this extended green diagonal, and we have expressed AC prime then into AO plus OC, AO plus OC prime. So that is what we have done, AO plus OC prime. But since AO is equal to AC, we have replaced this AO with AC and OC prime, and therefore when we do that, the strain along the AC is the ratio of OC prime by AC. Now when you consider this AC here, so AC here is the diagonal of the square ABCD. So the AC here is the diagonal of the square ABCD. So therefore the AC is nothing but square root of BC. The AC that we have considered, this AC here, is nothing but the diagonal of ABCD. So therefore this AC can be written as square root of the one of the equal sides. We will consider the side BC, so it is square root of BC. So AC can be expressed as square root of BC. Now we have a section called OC prime. Now there is this triangle here. We have a section called OC prime, and this OC prime, this section called OC prime, is a part of this triangle, which is a right angle triangle. So we have a right angle triangle, and we have a part of this triangle that describes the strain AC. Now when you consider the original sample, that is A, B, C, D, the angle here, the angle in this region can be treated as theta. So angle in this region can be treated as theta, which is equal to 45 degrees. So we have a square, a regular square, and in that square we have a diagonal. This diagonal splits the square, particularly this angle here, into two equal parts. So we have a square and we have a diagonal, and this diagonal splits the angle at C into two equal parts. So at C, the original angle is 90 degree, the diagonal splits the angle into two equal parts, so therefore the theta assumes a value of 45 degree. Now, since we are within the elastic limit, we are operating, or we are discussing within the elastic limit, and since the distortion or the change in the angle because of this new diagonal is limited, this angle will also assume more or less the same value. So this angle will be also be of the same value because we are restricting ourselves to the elastic region. So what we have is, we have an angle 45 degrees that is subscribed because of the diagonal. And now, since we are working within the framework of elastic deformation, the same angle is assumed in this region here. So in this right angle triangle that is highlighted in green, so that is in this right angle triangle, one of the angle is 45 degrees. So now when you consider cos of this angle, cos of this angle theta, the cos of this angle theta, since theta is 45 degrees, it is 1 by root 2, and it is nothing but, this cos of this angle theta is nothing but OC by CC prime. So OC prime by CC prime. So what we have done is, in order to express this OC prime in a different way, we have considered this right angle triangle, and we have considered the theta, the cos theta of one of the angles in this right angle triangle. This angle is 45 degrees because we are operating within the elastic limit, so the distortion is not much. So whatever angle we find here will be equal to the angle that we find here. This angle is 45 degree because it's a part of the diagonal that splits the angle at C into 2. So therefore this angle is also 45 degrees. So now when you consider cos theta of this angle within this triangle, then we are able to relate OC prime to CC prime. Now then the OC prime that we are interested in is of the form CC prime by root 2. Now we have an expression for AC, we have an expression for OC prime. So when we substitute these two in this expression here, so we have an expression for AC, we have an expression for OC prime. So then the strain along AC would be CC prime by 2BC. So we have substituted, so this will take the numerator and this will become the denominator, and when we do that, we end up with an expression of this sort. Now focus on this term here, that is CC prime by PC. When you focus on this term, that is CC prime by PC, so we have CC prime here, so let's use blue. So we have CC prime here, so this is CC prime, and BC is this one. So what essentially we have is, we have this expression CC prime by BC, which is nothing but the shear strain that we observe. So CC prime by BC is nothing but the shear strain that we observe, that we have already expressed. So therefore the strain along AC is nothing but 1 by 2 of the shear strain that we observe in the sample. So the strain along AC is nothing but 1 by 2 of the shear strain that we observe. Now we already have arrived at an expression for the strain along AC. So the strain along AC, we have already arrived at an expression. So this expression is the shear stress by the Young's modulus and 1 plus mu, that is the Poisson's effect, and 1 by 2. So this we are equating now to the shear strain. So we already arrived at an expression for the strain, and this strain we observe that it is nothing but the half of the shear strain that we observe. And now we have substituted this expression that we have already derived, and we now have a relation, an expression that relates shear stress, shear strain to the Young's modulus and Poisson's ratio. Now all we need to do is rearrange this expression in such a way that when we rearrange an expression, we end up having something of this sort. So when we rearrange it, so this is the expression that we get. And what we have is, here we have the ratio of the shear stress and the shear strain. So therefore this can be replaced by Young's modulus. So here we have the ratio of the shear stress and shear strain. So ultimately the expression that relates the shear modulus to that of the Young's modulus is of this form here. Yeah, so ultimately now we have arrived at an expression that relates the shear modulus to that of the Young's modulus. Now of course it has been quite a derivation, I understand that, but it is vitally important for us to understand these different relations and the key features here. So it can, even though the derivation is quite complicated, the key features are rather straightforward. We have identified a sample, and that sample, we have identified a sample or an element within a given sample that has experienced a deformation similar to what we experienced during tensile and compressive loading. And we have considered the deformation along the one element that has exhibited an elongation. And this elongation is due to two factors. One is direct loading, the other is the Poisson's effect. So the Poisson's effect is because of the other perpendicular element that is experiencing a compressive loading. And the direct effect is due to the shear stress. So we have combined these two and arrived at an expression for the strain along this element, the diagonal element that we are interested in. Now once we have arrived at the strain along the diagonal element, then we move back to our original sample and we attempted to quantify the shear strain with respect to the element that we are interested in, because we need to relate these two. So we focused on the shear strain, we arrived at an expression for the shear strain based on this element that we are interested in, and using that we were able to arrive at this rather straightforward looking expression. But these are all those steps we need to take to arrive at this expression. Now what we have been able to do thus far is, we have been able to relate the bulk modulus to the Young's modulus, and now we are able to relate the shear modulus to the Young's modulus. So ultimately it is possible for us to relate all these two together. Now it is possible for us, we are in a position to relate all these different moduli together. So with this, I understand that has been a bit of a longer lecture than ones that we usually have, but this is a critical one, so I didn't mind using your time, so please pardon me there. We will build on this understanding in the subsequent lectures. Goodbye.